So we are going to start the second chapter today, and we are going to do around half of this chapter today and continue this next week. And in this chapter, we are going to start the discussion of operational amplifiers. Last week, we discussed the discussion of general amplifier. What are the different parameters of general amplifier, including input resistance, output resistance, open loop gain, what we call intrinsic gain. In this case, in this chapter, we are going to focus on operational amplifier, because that's what the course is about, applications of operational amplifier. So some of the history of operational amplifier, as you can see on your screen, it's a very old device. In 1940s, it was created by Bell Labs, and initially, vacuum tubes and all those things. And in 1958 and 63, basically using solid state electronics, it was created as an IC. So in 1968, the operational amplifier that you're going to use, actually, that's how old this device is, but you still use it because it works. And it's a relatively small device. And of course, when you're integrating this on a big circuit, then it becomes even smaller. And this IC is applied in many applications. And most of the applications that we're going to discuss in this, they are very practical application, this course. And you will see those applications. Some of you have applied those applications in your senior design as well, especially active filters. This is an 8-pin IC that we are going to use in labs, operational amplifier. And this is the internal circuitry of operational amplifier. Now, again, I'm just showing it to you, the internal circuitry. We are not really going to be doing any sort of circuit analysis or anything on this. And you should be very thankful about that, because you can see this circuit. It's not easy. There are a bunch of transistors, as you can see, BJTs, resistors, and all those things. Observe, of course, that operational amplifier is a differential amplifier. It has two inputs where you connect your signal. You have the biasing, of course, V positive and V negative. These are two biasing, positive and negative. And then you have the two inputs, as you can see on top, which is what we call the positive input and negative input, which are the inverting input. The negative input is called inverting input, and positive input is called non-inverting input. Now, don't confuse those inputs with biasing. Biasing is different. Biasing is DC voltage. What you have to bias the IC is the DC voltage. The input signal is usually the AC voltage. Like in the quiz, you saw that you have 10 millivolt sinusoidal waveform. That is the input of your operational amplifier, which is the AC voltage. Now, biasing is done usually, we choose 15 and minus 15 for most of the labs. We're going to use 15 and minus 15 volt for the biasing. And the input depends upon, of course, different sinusoidal signal or square wave or triangular wave or whatever signal we are trying to amplify, sound wave and all those things. The IC that you're going to use is 741 IC. You will see a dot, basically, that represents that the pin on the left side of the dot is number 1, and it goes 1, 2, 3, 4, and on the other side 5, 6, 7, 8. Similar to how you have used in your digital circuit, different ICs that you have used in digital circuit. That's how the pin layout goes. On the left side, go down, and on the right side, go up. You're not going to be using all the pins. So number 2 is the inverting input. You're going to be using this. Number 3 is the non-inverting input. You're going to be using this. So 2 and 3. Pin number 4 is the negative biasing. So you're going to be using pin number 4 to bias the negative 15 volt. You're not going to be using pin number 1. That's offset null. Pin number 5 is offset null. You're not going to be using that. Pin number 6 is the output of the circuit. And pin number 7 is the positive biasing. And pin number 8 is not connected. So 1, 5, and 8, these pins are not generally used. And rest of the pins, 2, 3, 4, 6, and 7, those you're going to be using. Simplified circuit of the amplifier. operational amplifier looks like this. That's how we're going to be drawing in most of our circuits. You have the non-inverting input, inverting input, and the output. Since biasing does not change, so we don't really show the biasing on the circuit. So instead of showing all 5 pins, we don't really need to show biasing. But if you do have to show biasing, or when you're doing, of course, your simulation and you have to connect the biasing, then biasing is generally in the simulation. In the 741 IC in PSpice, you're going to see biasing voltages are going to be here, right here. So you're going to see V negative and V positive, V negative and V positive. When you pull the IC in PSpice, usually the positive voltage is going to be on top and negative voltage at the bottom. So just make sure to connect it correctly, because most of the time, all the circuits that we are using, usually we show that the inverting input is on top and non-inverting input is at the bottom. But when you pull the IC 741 in PSpice, it's going to be opposite. So just make sure you connect it correctly. Don't connect the negative, the non-inverting voltage to the inverting stuff and vice versa. So in circuits that we will be doing in the class, of course, as I said, you don't really need to show the biasing voltage. All you need to show is the non-inverting input, inverting input, non-inverting input, and the output. In simulation, of course, you will have to have all 5 pins, and they will be connected to their respective voltages and system. So I guess I discussed all voltages and stuff. Some of the applications, it's used in audio amplifier, regulators, active filters, medical sensor interfaces, baseband receiver, analog to digital converters. Actually, since many of you are in the DSP class as well, when we discuss analog to digital converters tomorrow, flash ADC, you will see that in flash ADC, operational amplifiers are used. Oscillators, signal generators, hearing aids, so many applications for operational amplifier that you will see in this course and you can see in practice. Most of the, now from chapter number 1, we discussed an amplifier has what? An input resistance, an output resistance, and an intrinsic gain, what we call open loop gain. All right, observe in that amplifier symbol, I put the input resistance, Ri, I put an output resistance, and of course, you have an intrinsic gain over here multiplied by the input. So let me go ahead and put my red marker. The input voltage that you're supplying is what we call the differential voltage, the difference between the non-inverting input and inverting input. That's the input of the operational amplifier. And it's called the differential input. It's a differential amplifier, which is the difference between Vp minus Vn. That voltage is applied. It's applied across the input resistance. This is the input resistance Ri. This is the output resistance Rout. And this is your input voltage, which is the differential voltage multiplied by the open loop gain. So it's very small, so I'm going to write down. This is A times Vd, or A times the non-inverting voltage minus the inverting voltage, and this is the output of your amplifier. Well, this is the output of this, basically. And then, of course, some voltage is going to drop in R0, and then the output is going to be here. Let's go ahead. Now, when we are discussing ideal operational amplifier, this is the characteristic of operational amplifier, or these are the characteristics of operational amplifier. That's why it is such a nice device to use. And the characteristics, and you're going to see these ideal characteristics are very similar to practical characteristics when we discuss chapter number 3. The ideal characteristics of operational amplifier is the input resistance is extremely large. Hence, ideally, we assume it is equal to infinity. Our input is extremely large, we assume it to be approximately infinity. And that's what we want actually for a perfect amplifier. The output resistance is very small. Practical resistance, as you will see again, chapter number 3, you can see in the data sheet, it is very small value. And therefore, we assume it to be 0. And the gain, intrinsic gain of the amplifier A is extremely large. And again, ideally, we assume it to be, again, infinity. So these are our assumptions for the ideal amplifier. The open loop gain or intrinsic gain is assumed to be infinity. The output resistance is very small, assumed to be almost 0 or short circuit. And the input resistance right here is extremely large, and it is assumed to be open circuit, or it is assumed to be infinity. That is, it is an open circuit. And these are very practical approaches for the calculation of different quantities in an operational amplifier. Again, you will see these in chapter 3 when you find the exact values, and you will see, well, these exact values are just too large that we can really use the ideal values, and we're not going to lose anything as far as precision is concerned. So assuming all these ideal cases, our operational amplifier is going to be reduced to the input resistance, which is open circuit, and the output resistance, which is short circuit. And of course, your gain is infinity or almost infinity, but you just show the gain value. You just show the dependent source over there, gain times VD, which is V positive minus V negative. Now, this gain provides another extremely important characteristic of operational amplifier, and that characteristic is right here. So A times VD is equal to V out. As you can see, V out, assuming R naught is equal to 0, very small output resistance, then A times VD is equal to V out. So V out is A times VD is equal to V out, and V out over A is equal to VD. So V out over A is equal to VD. And again, VD is the difference between the non-inverting input and the inverting input. And since A tends to infinity, A value is very large, we apply a limit A tends to infinity, V out over A, which is equal to V positive minus V negative. So V out over A is going to be approximately equal to 0 when you apply the limit, and A becomes extremely large. So if A becomes extremely large, close to the limit, this thing is going to be approximately equal to 0. So V positive minus V negative will be equal to approximately 0, which means that V positive is equal to V negative. This is an extremely important result when we are analyzing circuits with operational amplifier. And this result tells us that whatever voltage you're going to find at the non-inverting input, the same voltage you're going to find at the inverting input of the operational amplifier. So this is true for practical circuits, as you will see. So the inverting input voltage is the same as the non-inverting input voltage. So V positive is equal to V negative, and since the input resistance is infinity, it's open circuit, really there is no current that flows into the operational amplifier either from positive side or the negative side. So ideally, the positive current going into the positive terminal and the negative terminal both are equal to 0. Ideally, there's a small biasing current, as we're going to discuss. But generally, there is no current that flows into the operational amplifier. So these again results are used when we are analyzing different circuits that are based on op amp. Okay. Now, any operational amplifier, when you bias them, so let's say this is your operational amplifier. This is your V negative, V positive, V out, and I can show the biasing voltage as well. Let's say this is your positive VCC, we call it VCC. So positive VCC and negative VCC. Now, positive and negative VCC provides you the maximum voltage gain that the operational amplifier circuit can provide you. You cannot exceed that value. So if you are biasing this with 15 volt and negative 15 volt, then on the positive side of the amplified waveform, it cannot exceed 15 volt. And on the negative side, it cannot exceed negative 15 volt, because that's the maximum. DC provide the maximum value. Let's assume your gain is very large. Like for example, in today's quiz, your output voltage was what, 41 point something, right? 41.8 or something like that. Let's say that amplifier you biased with 15 volt and negative 15 volt. So the maximum swing you can have about 30 volt, 15 and negative 15. And the output voltage is coming out to be 41.89 volt or so. That means as soon as that, and let's say that output voltage is centered right at 0. So you have about 20 volt on the positive side, 20.5 volt on the positive side, and negative 20.5 volt on the negative side. As soon as that voltage is going to exceed 15 volt, it is going to be clipped and become saturated, because it cannot exceed 15 volt. And likewise, as soon as it will exceed the negative side, it's going to clip, and this will keep on going. So it will not go beyond 15 volt, and it will not go beyond negative 15 volt. So you're never going to achieve 41.89 volt amplification from the circuit. Real circuit. Of course, in the quiz, we did not assume all those things, right? But if I tell you that, hey, your biasing is 15 and negative 15 volt, tell me what will be your output voltage. And as soon as you see that, oh, my output voltage is 41.89 volt, then your answer should be, since the output voltage exceeds 30 volt peak to peak, the output voltage is going to be the maximum value, that is 15 volt in the positive side and 15 on the negative side. It's going to just clip at that value. It's not going to be 41 volt in the practical circuit. Of course, in the quiz, we say 41 volt. That's fine, because we did not mention any saturation or anything at that time. But this is what you're going to observe in your lab as well, when you're going to keep increasing the input voltage, and at that some time you will see that the output starts saturating, which is close to 15 volt. It's not going to be at 15 volt. It's going to be close to 15 volt, because your DC biasing levels will be 15 and negative 15. Now, saturation poses a very difficult situation when you're using the operational amplifier in what we call open loop configuration. And there are actually applications of open loop configuration, as we're going to study in chapter 6. But amplification, when you want to do amplification, you don't use it in the open loop configuration. What is open loop configuration? Using amplifier without any feedback resistor. That is, no resistor going from the output to the input. Or, in other words, you are using the intrinsic gain of the amplifier, which is A, to amplify the input, which is VD. That's called open loop configuration. So you are using A times VD, and you're trying to provide the output. So remember, this is your VD, positive, negative, and this is providing you the output, and output is A times VD. A is the intrinsic gain or open loop gain of the operational amplifier. Now, there's a problem here, because A, again, the practical value of A is 200,000 in the data sheet. When you will see, the nominal value is 200,000 for A. Again, we assume it to be infinity, ideally, but it's about 200,000. With the value of 200,000 of A, any small value of VD, it's usually 69 millivolt. 69 millivolt times 200,000 is like 15 volt or something, if I remember correctly. Any small value of VD is going to push the output to saturation. Because if the gain is 200,000 and you put even 1 volt, let's say, at the input, then the output is going to be 200,000. Now, output cannot exceed 15 and negative 15. That is the biasing limit if you're biasing at 15 and minus 15. That means any small input that you're going to take is going to push the output to saturation. And your output will never be properly amplified. It's just going to be always saturated. So we do not use, when it comes down to the amplification, we do not use the operational amplifier in the open loop configuration. That is, we do not take the advantage of the open loop gain A. We set our own gain for the operational amplifier. And we use the amplifier in what we call closed loop configuration. So most of our circuits, amplifier circuits that we're going to discuss, they're based on closed loop configuration. Now, again, towards chapter 6, or when we discuss oscillators, that's when you use amplifier in an open loop configuration. So oscillators are basically, they're going to oscillate, like they're going to produce a square wave oscillators between maximum value and minimum value. That's when you use the amplifier in an open loop configuration, because any input that exceeds a small value, the output is going to be either positive 15 or negative 15. So when it comes down to oscillators, we use this as an open loop configuration, but when we use it as an amplifier, we use it in a closed loop configuration, and we set our own gain, as most of the discussion is going to revolve around today and in other applications. The first closed loop application of amplifier are very commonly used amplifier, what we call inverting amplifier. Inverting amplifier, as you will see, the name implies, it's called inverting amplifier because the output and input, they have a phase difference of 180 degrees. So output is an inverted form of the input. 180 degrees means when your input is high, the output is low, and when the input is low, output is high. So the phase difference between the two is 180 degrees. And that's why it's called inverting amplifier. But how to identify the inverting amplifier? To identify the inverting amplifier, you will see that the input voltage is applied to the, it's connected to the inverting input of the operational amplifier. So when input voltage is connected to the inverting input, it is an inverting amplifier. But the name inverting comes from the relationship between output and input, as you will see. So this is the circuit of inverting amplifier, and this circuit is not going to change if you are using inverting amplifier. You have the input resistance. Now this is not the input resistance of this is the input resistance of the circuit, but we're just calling it Ri. In this case, Ri will also be the input resistance of the circuit. And this is your Rf, which is the feedback resistor. Now, if I ask you drive the gain of the circuit, then you're going to do the derivation. You're not going to just give me the equation. How do we drive it? Now we use the assumption that the non-inverting input voltage and inverting input voltage, they are assumed to be equal. That's our first assumption, as we discussed a few slides back. And the second assumption is, of course, that the positive current and the negative current, both of them are zero, because the input resistance of the operational amplifier is extremely large and we assume it to be open circuit. So current cannot go in the input through the input resistance. We're going to use these two assumptions. The first assumption, V positive is equal to V negative. Now V positive is connected to ground. That means our V negative value is also 0. Right? Any voltage that is going to appear at the non-inverting input, we will assume the same voltage at the inverting inputs. In this case, your inverting input is called virtual ground because it's not connected directly to the ground, but it has the voltage of 0. So it is called virtual ground in the circuit. This is called virtual ground. And the second condition is that no current goes inside the operational amplifier. That means the current that is flowing from the input voltage towards the inverting input, that current cannot go inside the inverting input. Means that this current is going to divert through the feedback resistance and go towards the feedback resistance. So I input is equal to I input is equal to IF. If you apply KCL at the non-inverting input, at the inverting input, then I input will be equal to IF because no current is going, I negative is equal to 0. If you apply KCL at this point, and if we assume that this is the current I negative, then KCL at the inverting input, KCL at the inverting input is going to give you I input is going towards the node and I negative plus IF, they are going away from the node. But since I negative is 0, that means I input is equal to IF. So this current and this current, they are going to be equal to each other because there is no current that is flowing into the operational amplifier. And that derivation is shown over here. So I input is equal to IF. I input is going to be V input minus V negative, which is 0, divided by R input, Ohm's law. V input minus 0 divided by Ri. V input minus 0 over Ri. And IF, again Ohm's law, 0 minus V out over Rf. 0 minus V out over Rf. And that's what you see over here. V input minus 0 over Ri, or V input over Ri, is equal to 0 minus V out over Rf, or negative V out over Rf, which will give you V out to be negative Rf over V input. And that will give you the closed loop gain expression V out over V input, which is negative Rf over Rin. So that's the closed loop gain equation that you can modify because it depends on the two resistors that are connected in the feedback loop and in the input path, Rf and Ri. So you can change, if you change those resistors, your closed loop gain is going to change and your output is going to change based upon your input. Now the gain is Rf over Ri. That's the gain value. Negative sign just tells you that the output and input are 180 degrees out of phase. When output is high, input is low. When input is low, output is high. So that negative sign is basically 180 degrees out of phase between input and output. And the gain of the amplifier is Rf over Ri or R1, whatever it is. Ri, I think, is Ri. And observe that you don't have any open loop gain in that expression. It's independent of open loop gain. So in this case, V out is equal to negative RF over RI V input. Once you set the closed loop gain, then you can get any output value based upon any input value multiplied by that closed loop gain. And of course, input and output are going to be 180 degrees out of phase because of that negative sign. If you want to change it, RF and RI, the gain is going to be changed. Of course, there's going to be a limit that you can change up to because of the saturation. So if you cannot just keep changing RF, let's say RI is 1 kilo ohm, and you say I will keep increasing RF and my output will keep on increasing. That's not going to happen because once it will hit saturation, the output is just going to become flat. It's not going to keep on increasing. So there will be a limit to which you can change the values of RF and RI in order to have the output below saturation level. So this is your first amplifier application, which is very common application. So keep that in mind. If I ask you to do the derivation, this is the derivation that I showed you. Apply KCL at this node right here at the virtual node. Very simple derivation, KCL at inverting input. I input is equal to IF, and then write Ohm's law for both IF and I input. And from that Ohm's law, you will find the relationship of the input and output voltages. Okay, let's go ahead and take a break now and then continue our discussion after the break. All right, guys, so we're going to go ahead and continue with discussion of inverting amplifier. So a couple of last things about the inverting amplifier. Every amplifier or every circuit, every electronic circuit, it has an input resistance. Input resistance means that the ratio of the input voltage to the input current. So what you have over here, this circuit, you have the input voltage between the inverting input and the ground, and of course the input current is going that is coming out of the input voltage. The ratio between these two is considered as the input resistance of the circuit, and in this case, the input resistance is the same as your resistance that is connected between the input voltage and the inverting terminal of the operational amplifier, because using Ohm's law, I input is equal to V input over R input, since you have a virtual ground over here. So I input is Vi minus 0 over R input, which means the input resistance is V input over I input, which is the same as your resistance that is connected between the input voltage and the inverting terminal. So this is the input resistance of the circuit, of the inverting amplifier circuit. Sometime a circuit may have the input resistance which is similar to what is connected, as you can see in this case, and sometime it may have different input resistance. In this case, the input resistance is the same as connected between the input terminal and the inverting terminal of the operational amplifier. And this is just a graph to show the relationship between the input and output of an inverting amplifier with a gain of 2. So if your RF over RI is 2, and if you're giving a sinusoidal input with a peak value of 1, the output of the inverting amplifier is going to look like this. So the output peak value is going to be 2, which is gain times the peak value of the input, and observe that the phase difference between the two is 180 degrees, which is the negative sign that you saw in the equation, negative RF over RI. When input is high, the output is low, and vice versa. So when you do the lab, the first lab, you're going to see this type of output, the relationship 180 degree out of phase relationship between the input and output. The second important amplifier that is very commonly used is non-inverting amplifier. And as the name suggests, the input and output, they are not, they don't have any phase difference. The input, when it is peak, the output is going to peak at the same time. So there is no 180 degree phase difference in non-inverting amplifier. How do you recognize if it's a non-inverting amplifier? Input is connected to the non-inverting terminal of the operational amplifier, V positive. And then you have a resistor Ri here, a resistor Rf here. And once again, when you're doing the derivation, you can apply any direction of current, doesn't really matter if you're applying this direction or any other direction. All you have to do is to apply KCL at the inverting terminal. So remember, this is the inverting terminal, this is the non-inverting terminal. Now, since Vi is applied at the non-inverting terminal and using the relationship or the approximation, sorry, that the negative input and the positive input, they are the same ideally, we will assume that at the negative input, the same voltage is going to appear, which is V input. So the voltage here is going to be the same as this. Although this is not connected to the input source, but due to the approximations and the ideal characteristics that we have studied, at the non-inverting input, when we apply V, the source voltage, the same voltage is going to appear at the inverting input. And then you're going to apply the KCL at this node to determine the relationship between the output and the input voltage and the overall gain. So when you apply KCL, the two currents are going to be the same because there is no current that is going to go in the input terminal of the operational amplifier. We already declared that no current goes in the input terminals of the operational amplifier because of the extremely high input resistance of the operational amplifier. So these two current IF and II, they will be equal to each other. Current going towards the inverting terminal is equal to current going away from the inverting terminal. So IF will be equal to II. And again, you're just going to apply Ohm's law. For IF, Ohm's law is going to be V out minus Vi over Rf. And for II, this current, apply Ohm's law, again, Vi minus 0 over Ri. And from that, you can write down V out over Rf. And since Vi, there are two terms, I'm going to take this Vi term on the other side. Vi over Rf plus Vi over Ri. And then I can write down V out over Vi, take Rf on the other side. This is Rf. Rf over Rf plus Rf over Ri. So the closed loop gain, which is the output over input, in this case is going to be 1 plus Rf over Ri. And this is the derivation that is here. And that's how you do the derivation of the non-inverting amplifier to get the gain expression, closed loop gain expression. If you have any question, please ask me. Again, it's given over here. I just did it in front of you again. So all you are doing is you are assuming the ideal condition, and then you're applying KCL at the inverting input, inverting node, and applying Ohm's law. That's all you're doing. So the closed loop gain of the non-inverting amplifier is 1 plus Rf over Ri. Observe, there is no negative sign. That means the input and the output, they will be amplified, but they will not have any phase difference between the two of them. Phase will be the same. One of the special cases of non-inverting amplifier is the voltage follower. That is, the output is going to be whatever the input is. In this case, you're applying your input voltage at the non-inverting input, right here or right here. And either you have a resistor over here or you have a short circuit over here, doesn't really matter. But the important thing is that this resistor value and this resistor value must be exactly the same. In this case, my Ri, if I want to show it, I'm assuming this Ri to be almost infinity, extremely large, and that's why it is shown as an open circuit. So assuming that Ri is an open circuit, it's extremely large, and gain of the amplifier is 1 plus Rf over Ri, the non-inverting amplifier. If Ri is open circuit or extremely large, then when you take the limit Ri tends to infinity, this is going to be 0, and your ACL, the closed loop gain, is going to be approximately equal to 1 or 1, which means that the output and input are going to be equal to each other in this case. So this circuit is called voltage follower circuit. That is, the output is going to follow the input, exactly the same value with a gain of 1. If a gain of 1, the question is, why do we use it? I mean, why do we use a circuit that the output is equal to input? Why don't we just connect the input directly to the output? And in many applications, we want to isolate the output from the input, such that when you connect a load at the output, it does not it does not load down the input value. That is, by varying the load at the output, sometimes it happens that the input value also starts changing because of the input resistance, the source resistance. The current is flowing through the source resistance, and input value can start changing. So when you want to isolate the output and the input but want to keep the same value, then generally voltage follower circuit is used. So any voltage, any load that you are connecting at the output, load will be connected right over here. Any load that you're connecting at the output, RL, that value of the load is not going to change the input of the voltage follower, irrespective of what value you are using. So for those for those circuits where it is very important that the output is exactly the same as the input, irrespective of the load value, this type of circuit can be used, which is the voltage follower circuit. All right, some examples. Let me move this here. Non-inverting amplifier is shown in this figure. If output saturates at positive negative 13 volt, calculate the maximum value of the input sinusoidal voltage for amplification. Calculate the output current when the input is maximum. Okay, so this is a non-inverting amplifier. We have 5 kilo ohm R1, 100 kilo ohm R2, and we have also a load connected, which is 10 kilo ohm resistor. So you want to know what is the maximum value of this maximum value of the input sinusoidal. So this is the input sinusoidal voltage connected right here. That is going to produce the output just before it saturates. It saturates at positive negative 13 volt. So we know that this is a non-inverting amplifier, so the output is equal to 1 plus Rf, in this case is R2, so I'm going to write down R2 over R1 times V in. That's our equation for non-inverting amplifier that we derived over here. V out is equal to 1 plus Rf over R input times V input. and V input is equal to V out over 1 plus R2 over R. Now, since the saturation happens at 13 volt, you can find the value of the input that will make the output go up to 13 volt. One plus R2 is 100K and then 5K, so 100 over 5. $13 over 1 plus 100 over 5. .619 or 619 millivolt. So the input value of 619 millivolt is going to push the output to 13 volt. Any value of the input which is more than 619 millivolt peak value is going to make the output to be saturated, because this is this value is going to take it to 13 volt, and any value more than that is going to make the top flat and the bottom flat. So there's a maximum value allowed to get to 13 volt. Any input value greater than 619 millivolt will saturate the output voltage. Make sense? So that's part number one. What is the maximum value of the input for which the output is going to saturate? Or maximum value for the amplification. Any value greater than this is going to output is going to saturate. Calculate the output current when input is maximum. That is when input is 619 millivolt. What is the value for the output current I out? This is I out right here. This is part one. Okay, so this value, this is the I out. What is the value of this current when the input voltage is 619 millivolt? We can easily find this. We know where the input is 619 millivolt, output is going to be 13 volt. So we know this voltage. We know R2, we know RL. That means we can calculate I2 and we can calculate IL. So we can easily calculate I out using KCL. What will be KCL at the output node? IL is going away and I2 and I naught are going towards. So IL is equal to I2 plus I out at the output node. And since we have to find I out, we'll keep I out on one side and write down IL minus I2. All right, IL is the current through the load, which is V out over R load. So V out over R load. And I2 is the current passing through the feedback resistor, which is your V input, since the voltage at this node is going to be V input. V input minus V output over R2. So go ahead and calculate and let me know. Input in this case is the maximum voltage, which is 619 millivolt, and the output, of course, is going to be 13 volt. Calculate what will be the value of the current, output current. How much? 1.42 milliampere. Okay. 1.42. Anyone else getting the same value? You got the same value? Okay. So 1.42 milliampere is going to be the current coming out of the operational amplifier when the input is the maximum value allowed, which is 619 millivolt. And of course, at that time, the output is going to be 13 volt. Any question, guys, on this? Note that any voltage more than 1619 millivolt will push the output deep into saturation, as we discussed, and it will start becoming squarish instead of sinusoidal. When this will happen, then we will no longer consider the output as an amplified version of the input, as the shape of the output is going to be different from the shape of the input. All right, second example. For the following circuit, determine the peak output voltage of the amplifier. So the input voltage is given, peak value, small, so let me write it down. 100 millivolt peak value is given. And we want to know what will be the output voltage corresponding to this value. What type of amplifier do we have, inverting or non-inverting? We have the non-inverting amplifier because you are applying the voltage at the non-inverting input. But observe that Vs is not applied at the non-inverting input. The voltage that is applied at the non-inverting input is Vi, as you can see over here, this Vi, which is the voltage across this resistor. That's what's applied at the input. Again, there's no current going into the inverting input terminal and non-inverting input terminal and inverting input. So there's no voltage drop in this resistance. So whatever voltage you will see here at this node across this resistor is going to be the voltage that is applied at the non-inverting input terminal, because no voltage is going to be dropped in that R6 resistor or whatever that resistor is. So what will be the voltage Vi? So this I positive is equal to 0. What is the voltage at Vi? How are we going to calculate that? Voltage division simply between R3 and R2. That's R3 and R2. Voltage division across voltage across R3 is the voltage division between R3 and R2. So V input is equal to R3 plus R2 times Vs. Right. 100 millivolt R3 is 6 over 2. So 6 divided by 8 times 100. How much? 75 millivolts. So that's your input voltage. That's the peak value of the input voltage. Peak value of the source voltage is 100 millivolt. Peak value of the input voltage, input to the circuit, is 75 millivolts. So for this, we're going to find out what is the output voltage. The output voltage, since it is non-inverting amplifier, the output voltage is simply 1 plus RF over RI times the input voltage. RF is 99 kilo ohm, RI is 1 kilo ohm. So 1 plus 99 K over 1 K will be 99 times 75 milli. So 100 times 75 milli. That is going to give you 7500 millivolt or 7.5. .5 volt is going to be the peak value of the output voltage. Slide. Yes. What is that? Yeah, in the equation I just put R2, so I just changed that to R2 basically. Oh yeah, I don't know if it was R1 or R2, whatever. In the equation I put down R3 over R3 plus R2, so I just changed the variable to R2 in the. Yeah. Okay, guys, any question about the two examples that we did? This one and this one. Yes. What is what? I'm sorry. RZ. What? Oh, that doesn't matter though. It doesn't matter because the current passing through it is 0. So you don't have any drop through that resistance, remember. So that's why you don't see any value for that input resistance, right? It's not going to do anything in the circuit. Yeah, it's bias compensation resistor, what we're going to discuss next. Yeah. All right, guys. So one of the things that is just a matter of discussion. We don't really use that when we're solving circuits and stuff. But the concept of bias compensation resistor. So we know that for the ideal case that we've been studying so far, we assume that no current goes in the inverting terminal and non-inverting terminal. We assume that to be 0 because the input resistance is extremely large, almost infinity, so the current doesn't pass through that. So that's what we have discussed so far. But operational amplifier, as you saw earlier, the picture of operational amplifier and the input, they have bipolar junction transistors. And those bipolar junction transistors, they do have some current going through their bases at the input. And those current, because of the biasing of the circuit, positive and negative biasing, you have some sort of base current going in the circuit, which are the bias currents. And they are very small usually, typically in nanoampere. But what happens when those current, bias current flows in the positive and the negative input or wherever, they can produce a small voltage at the output, and that's offset voltage or error voltage generally. So assume that you're not giving any input to the circuit. V input is 0, but when you measure the output voltage, you still see a very small output voltage at the output of the circuit. It's possible. And the reason for that is because of the biasing current. You may have some output voltage, which is again going to be extremely small biasing voltage. At the if it does appear, it's going to be an extremely small value. Even if your input voltage, the VD is 0, the difference voltage between the positive input and negative input is 0. So it's possible. So we need to take care of that. We want the output to be 0 when the input voltage is 0. The input differential voltage between the positive and negative input are 0. We want the output to be 0. We don't want it to have a small voltage at the output if there is any. So to take care of that problem, we use a resistor which is called bias compensation resistor. And that bias compensation resistor, there's a long discussion of that. I put the link over here. It's a really good discussion, and you can look at that. But in general, this is the summary of why there can be a small output voltage even if there is no input voltage, and why and how you can take care of that. Yes. It takes you restaurant page? Oh, so they changed that. Oh, this is the electronic devices circuit page. I'll have to go in and then find that link that it's again. It's interesting. They changed the link. Yep, it does go to a restaurant page. That's true. Okay. I'll have to find because this when I wrote the notes, that was the link where there were discussion of biasing current and all those things. And I did not really want to put all of those because again, there's something that's something that again there's really no need to discuss in detail because we don't really use that that much. So that's why I just put the link that if you are interested, you can read that. But they changed the link, so I'm going to go ahead and delete this here and then find the link and then discuss that. We'll find the new link. Okay, so where is bias compensation resistors? The two circuits that we discussed so far, inverting amplifier and non-inverting amplifier. That's where we put the bias compensation resistor. So that's where you see RC. That's the RC in that circuit, 2.2 example. That's what the bias compensation resistor. So it's connected in the non-inverting, in the inverting amplifier, it's connected towards the non-inverting input. And actually in both non-inverting and inverting, it's connected to the non-inverting input. And in general, it is taken as a parallel combination of these two resistors in both circuits. And once again, when we are solving the circuit, then we don't really consider that because we still solve it based on the assumption that our input current is 0. Input current going into the positive non-inverting terminal and the inverting terminal that's 0. So we putting that, assuming the current is 0 for the sinusoidal input, you don't really have any effect of these. This is only for the DC current, the biasing current, that we don't really care about that, but this helps taking care of that offset voltage and make it 0. So that's your RC, the bias compensation resistor. Voltage controlled current sources. So last chapter we discussed that amplifiers are, they act as controlled sources, voltage controlled current and voltage controlled voltage, current controlled voltage, and so on and so forth. So we're going to look at now some of the specific circuits of how to design these amplifiers as voltage controlled current sources and current controlled current sources. What's the idea of voltage controlled current sources? So the idea behind the voltage current control source is that if you connect a load, then the current through that load should be proportional to the input voltage, and it should not depend on the value of the load. That's the main idea of a voltage controlled current source, that the current that is passing through the load that you are connecting is independent of the value of the load. It only depends on the input voltage. So based on that idea, we have three circuits that we are going to discuss: floating load inverting voltage controlled current source, floating load non-inverting, and grounded load voltage controlled current source. The first circuit is floating load inverting voltage controlled current source, and this circuit is the same as the inverting amplifier, as you can see. But we are going to look at this circuit from a different angle, not from the angle of inverting amplifier, but from the angle of voltage controlled current source. We know we just did the derivation of this. Now in this case, load resistance is connected in the feedback loop. So this is your load resistance. Instead of calling it RF, we assume that this is the load resistance. And this is your input resistance, and we're just calling it R in this case. And of course, we assume no current goes in the input terminal. So this current II is equal to IL. IL is equal to II. And IL will be equal to V input over R. V input is this, V input over R, because this is virtual ground. So it is 0 volt here. So V input minus 0 over R is equal to the current coming out of the voltage source, V input, which means the load current will be equal to simply V input over R. And 1 over R we are calling as GM, which is transconductance, which is equal to 1 over R. So the load current can be given by GM times VI. GM, of course, is going to be a constant value as long as your resistor R is constant, which means that the load current just depends on the value of R. As long as it is constant, then the load current is going to just depend on the input voltage IL. And whatever value of RL is there, irrespective of what value of RL you're using, the load current is going to be independent of that value. As you can see, RL does not appear in this equation at all. So the same circuit, the inverting amplifier circuit, can be treated as a voltage controlled current source. The circuit, this circuit is going to work as linear voltage controlled current source as long as the output voltage does not saturate for any positive or negative input values. So we have to find the condition for which the output voltage must not saturate for any load value, and that condition is going to come from the output voltage. The output voltage, this current, load current, is 0 minus output voltage over RL using Ohm's law. 0 minus V out is equal to IL times RL, and V out will be equal to the absolute value of IL times RL. Absolute value because, positive and negative sides, any side that we are considering, we're just finding the value of that, not the positive and negative sign, but the value of the load current for which the output will still be less than saturation voltage. As long as it is less than saturation voltage, it is going to work as a voltage controlled current source. And that value we can get from this equation, that as long as the magnitude of the load current times the load resistance is less than the V saturation, then this circuit is going to act as a floating load inverting VCIS. And the range of this load current to satisfy this condition is called the dynamic range. Dynamic range of the circuit. The second circuit we're going to look at is the floating load non-inverting VCIS, voltage controlled current source. Now, floating load non-inverting is the same circuit as non-inverting amplifier, as you can see. Non-inverting amplifier. And again, we are just going to look at this circuit from a different perspective. From the perspective of a current source, voltage controlled current source. And again, we are assuming here that the feedback resistor is our load resistor. This is the load resistor, which is in the feedback loop. And this resistor is simply R. Input is applied at the non-inverting input terminal. So the same derivation that we did earlier, the voltage here is going to be VI. And again, these two currents will be same since no current is going to flow in the inverting input. So the load current, this is the load current, is equal to this current II, and the load current is going to be equal to VI over R using Ohm's law. And once again, we assume 1 over R is equal to Gm, which is the transconductance. So load current is again equal to Gm times Vi. As long as this R has a constant value, then the load current will simply be proportional to the input voltage. Thus, the circuit can also be assumed as the voltage controlled current source. When you change the voltage, the load current is going to change irrespective of the value of RL that is connected. However, again, we're going to find the dynamic range of the load current for which the circuit is going to operate properly. And that dynamic range is going to be the same way that we calculated the dynamic range of the last circuit, that is through the load current. So in this case, load current is equal to V out minus Vi over RL. Load current is V out minus Vi over RL. And from that, V out minus Vi is equal to IL times RL, and V out is equal to IL times RL plus V input. And we know that V input is equal to IL times R from this relationship 2.9. V input is IL times R. So IL times RL plus IL times R is equal to V out, which will give us IL times R plus RL. Which means that to find the dynamic range of the current, absolute value of IL times R plus RL must be less than the peak value or the maximum value at which the output will saturate, V saturation. So this value must be less than V saturation in order for the circuit to operate as a linear floating load non-inverting current source. Therefore, for the same values of resistor, the dynamic range of this circuit is lower than the floating load inverting VCIS. All right, why did I write down that statement? Who can explain it? The dynamic range of this circuit is smaller than the dynamic range of the circuit that we discussed previously, which was floating load inverting VCIS. Why is that? You have an extra resistor, yeah. So IL value must be smaller because when you take the product of this, the IL value has to be lower in order to achieve the same saturation voltage. So for this circuit, dynamic range of IL is going to be smaller than the dynamic range in the previous circuit. Grounded load VCIS. So the last two were floating loads, where load was not connected to the ground. And this one is grounded load VCIS. As you can see, the load is now connected to the ground. And that's why it is called grounded load VCIS. Load is connected to the ground. Okay, so how do you do the derivation of this? To show that the load current depends on the input voltage only, and it does not depend on the load resistance. In this case, first we observe that, of course, this current is 0. I negative is 0, as we assume, and I positive is 0. So we assume that for ideal cases. Whatever voltage you have on the inverting input terminal is going to be the same as the non-inverting. So at the inverting input terminal, we can find that the voltage is going to be half of your output voltage, because these two resistors are the same. So whatever voltage is going to be across this resistor is going to be the same across this resistor. Again, no current is flowing here. So this current, IF and II, they're the same. Same current is going through this branch. So half of the voltage will drop here and half of the voltage will be dropped here. So the voltage at this node is going to be exactly half of the output voltage, V out over 2. And that voltage is going to appear at the non-inverting input. At the non-inverting input, load resistor is connected. So whatever the voltage that appears here, that's the voltage, that is the voltage that appears across the load resistor. Therefore, the load voltage in this case is going to be half of the output. So this is the voltage across your load resistor, half of the output, which is the voltage at this node, as you can see, between this node and the ground. So now we know that the voltage there is half of the output. We can apply again KCL at the non-inverting input and find out the load current and the output voltage relationship. So we apply KCL at this node right here, which is right here. Apply KCL to the non-inverting input node. This is the non-inverting input. So this current is II, this current is IL, and this current is I2. I1 or I2, I don't know what I wrote down. I think it's I1 or II, whatever it is. So this current is equal to the load current. Load current is this IL, load current plus I2. So I1 is equal to IL plus I2. It's kind of small, but that's what I'm writing here. And since we have to find the relationship of IL, we write down IL is equal to I1 minus I2 or II minus I2. II using Ohm's law is going to be what? V input minus V load over R. This is V input minus V load over R. IL is simply VL over RL. And I2 is equal to VL minus V out over R. VL minus V out over R. These are the three currents. And those three equations are shown over here. IL is where is it? II, oh, right here. II is V1 minus VL over R. II is V1 or VI, whatever, minus VL over R. And then I2 is VL minus V naught over R. VL minus V naught over R, that's your I2. And that is equal to IL. And now we also know that VL is equal to half of V out. So we're going to go ahead and plug in this VL as half of V out. Or actually, we are trying to find out, let's see. Yeah, that's what we are doing over here. All right, so V1 over R minus VL over R minus VL over R, so minus 2 VL over R plus V out plus V out over R. Oh, we are changing V out to VL. Okay, so from here we are changing V out to 2 times VL. So our output, our equation is in terms of your V1 and VL in this case. So this 2 VLR and this negative 2 VL cancel each out, and our load current is equal to V input over R. That's what you see over here. Load current is equal to V input over R. It is V input, it's not V1. Sometimes I read it as V1, sometimes V input. This is V input over R, which shows that load current is directly proportional to the input voltage, and it does not depend on the value of the load resistor. Changing the value of the load resistor again is not going to change the load current because it only depends on the input voltage. And again, that's one of the characteristics of this source. It's also called by the way Howland current source. Grounded load VCIS is called Howland current source. If we find the dynamic range of the load current for which the circuit is going to operate properly, then we can do that again from here. Load current is equal to VL over RL, or VL is equal to IL times RL. And VL is half of V out, so V out over 2 is equal to IL times RL, or V out is equal to 2 times IL times RL. So for the circuit to operate linearly, the output has to be less than the saturation voltage. Therefore, the combination, the product of 2 times IL times RL has to be less than the saturation voltage. And from that, you can find out the dynamic range of this current for the circuit to operate linearly. Dynamic range of the current is half of the floating load inverting voltage current controlled current source. So these are our 3 voltage controlled current sources that we have to discuss. And these sources, your current is going to be dependent on the input voltage and irrespective of the load resistance. A Howland current source is to be designed with the current 1 milliampere. Saturation voltage is 13 volt and peak input voltage is 10 volt. Determine the value of R and the range for RL for linear operation. Okay. So input current, I input is 1 milliampere. V saturation is 13 volt, positive, negative. And input voltage is 10 volt. Input voltage is, determine the value of R for linear operation. Okay, so value of R first. We know that load current is equal to input voltage over R. Since load current is input voltage over R, we have to find R. So R is equal to V input over the load current. Oh, this is not the input current. This is designed for the current 1 milliampere. That's the load current that is given to you, not the input current. It is designed for the load current of 1 milliampere. So the resistance value R is going to be 10 over 1 milli, which is 10 kilo. These resistance value, there are 4 R's, remember? All of these R values are 10 kilo ohm in the circuit. If you are designing the circuit such that the load current is 1 milliampere for the input voltage of 10 volt. What is the value of RL for the linear operation? For the linear operation, output voltage has to be, load voltage has to be less than 13 volt. Two times the magnitude of the load current times RL has to be less than V saturation. That's the dynamic range that we discussed over here. 2 times the magnitude of the load current times RL has to be less than the saturation voltage. So RL for the boundary condition will be VSET over 2 times saturation voltage is 13 volt, and we are designing the circuit for 1 milliampere. 2 times 1 milliampere. 13 over 2 milli, which will be 6.5 kilo. So that's the boundary condition. That means any value of RL which is less or equal to 6.5 kilo ohm is going to make this source a voltage controlled current source. If this value exceeds beyond 6.5 kilo ohm, and if your IL is 1 milliampere, then of course this is going to exceed 13 volt and is no longer will be operated as in the linear zone. So the circuit is going to be invalid circuit for a current source. So for linear operation, RL has to be less or equal to 6.5 kilo ohm for a 1 milliampere load current source. At 10 volt input, of course. Okay, guys, question. Okay. All right. Well, according to the syllabus that I put together, I think this is perhaps the last topic that we were supposed to discuss today. I mean, we still have a lot of time. And how many slides are there? So next we have to discuss, let me see, current controlled voltage sources. and linear combination circuits, closed loop differential amplifier. We have a few more circuits to discuss, and we also have a lab that we are doing. So I think we can do that. We can just discuss it next week and then do the lab next week as well. So there's any question, by the way, so far? Okay, I'm just going to stop recording and then we'll discuss. Yes. For this, your peak voltage is 10 volt input. Yeah. No, peak input volt, because remember, voltage controlled current source, the load current depends only on the input voltage, not on the load resistor. So as you are changing the input voltage, the load current is changing. But if you're changing the load resistor, then the load current should not change. That's the whole idea of voltage controlled current source. The current source is depending on the input voltage. So at 10 volt, the current that you're designing the source for is 1 milliampere load current. And for that current, you are choosing or you are calculating different values of the resistor in the circuit. So in this case, RL is going to be 6.5 kilo ohm or less, well, less than 6.5 kilo ohm. Because if it exceeds 6.5 kilo ohm, then the output is going to become saturated, right? So any value below this is going to be fine. R has to be 10 kilo ohm, right? That value is going to be the same as long as you are, setting it for that input voltage. But you cannot exceed the value of 6.5 kilo ohm, otherwise it's not going to operate linear. Okay, let me stop recording and then we can discuss something about lab as well, actually.